Okay, so it should be recording now. So yeah, this is the final presentation of the EAWE Data Science Challenge 2024 to 2025. Welcome, everybody. So we've got 3 presentations today. Each will be 15 minutes each, plus 5 minutes of questions. If anyone wants to ask any questions, actually, so Gabrielle, you're the only, or maybe Osman as well, or you can ask each other questions. You can write questions in the chat, or you can just wait till the end of each presentation and then ask questions. So yeah, if you want to take over, Corin, then we can get going.
Okay. This one. Can you see my screen?
Yeah.
Nice. Okay, so right, I am mainly focused on sub-challenges number 1 and 2. And for that, I wrote a method or a code which focuses on the electrical torque versus rotor speed diagram we can see here in the background. And for that, I use the measurement values of the voltage and the current, and as well the low pass filtered rotor speed we have here. So my method is supposed to find the regions 1.5 to 3, the borders, and also the average lines, which we can see here. And based on those average lines and their intersections, as well as their slopes, there will be later the control parameters will be calculated based on those. Before I'm gonna implement my main method, I first decided to clean or filter the data. That means that I ignore all the outliers for the later method, and I excluded all the small torque and rotor speed values that are not necessary for this method. And then my method based this then on the binning strategy. So I divided the data along the rotor speed axis in a specific amount of bins, which is predefined. And I decided for 50 or 30. That seemed to be most reasonable. And on the right, you can see here 3 of those 50 bins. And the blue points we have here represent some measurement data. And those bins here serve as a way to mean or to calculate a mean for those average or for those measurement data, which then results in this line we can see here. And to also have a representative value along the rotor speed axis, we calculate the center, which then combined results in a coordinate which represents each bin, and then enables to compare those 2 coordinates and calculate a slope between those. And those slopes we can see here are the basis of the whole of the main method, which you can see in the next few slides. So as I said, my method focuses to find region borders and averages. And the main idea how I do this is to use the slope I've just showed you, or the slopes, or we are looking at one slope at a time. For example, for the point I, and we calculate the difference between the slope and the average of the preceding slopes in the current region we're looking at. And if this difference is higher than a predefined tolerance, that means that we have passed a region change. So what does this mean? I try to make it a bit more clear by using some figures we have down here. So we're going to start here with slope number 3, for example, which is this blue line here. And we're going to compare, or we are going to calculate the difference between the slope and the average of the preceding slopes, which is in this case the average between slope 1 and 2. And in this case, the method decides this difference is lower than the tolerance we have defined. So that means slope number 1 and slope number 2 are in the same region as slope number 3. Moving on to the next slope, slope 4 in this case, which is this slope up here. We again calculate the tolerance between the difference between slope 4 and the average of the preceding slopes. But this time, slope number 3 is also included in in this average. And also this time, this difference exceeds the tolerance we have predefined, which means the method says there is a region change between slope 3 and 4, and slope 4 is part of the next region. When we have finished this region, we will calculate then an average center and an average mean of each region, as well as an average slope. And we do this by using all the bins which are included in this region. And then we can calculate an average line for each region, which then is going to look like some of those lines we have here. How did I implement this in the code? I first created a list of parameters, starting with region start, which I set to 0 to begin at the very first point, and to set this as the first region start. And I created a parameter called mean slope region so far, which is the same parameter as here the S average of the preceding slopes. And I set this to the very first slope. Then I created an, at this time, still empty list of regions, and I defined my tolerance. So for each slope, as you can see here, or as you have already seen in the slide before, we are going to calculate the tolerance between the slope of this example point I, or in this case for each slope at the time, and then and the mean slope of the region so far. And if this difference is smaller than the tolerance, we include, as I already said, the slope in the mean slope of the region so far, which then serves as a new mean slope, and we move on to the next bin. If the tolerance is not observed, however, we close the region by setting a new region start on the point we're currently looking at, and we redefine, or we set a new mean slope of the region so far and use the slope I for that. So the first slope in the next region. And then this serves as the comparison slope for the next slope we're looking at. We then, as I said, calculate the average center, average mean, average slope for the closed region, and add those parameters to the list of the regions we have here created. Because this is not because it's not working as simple like this, I had to define special cases, and I also had to use correction strategies to make this method more flexible and universal to use it on different data. So here are my results for sub-challenge number 1 and 2. This might look a bit confusing on the first side, but I try to make it more clear. So the purpose of this slide is not only to show the results, but also to show where I extracted the results from. And you might recognize this picture here from the very first slide. Yeah, exactly. So starting with the cut-in speed down here, this is representing the intersection between the region 1.5 average line and the torque is equal to 0 line. The region 2 speed is extracted from the intersection between region 1.5 average line and the region 2 average line. And the same applies for those parameters down here, which uses the intersection with the torque is equal to 0 line and the region 2.5 average line. And up here, the intersection between the region 2.5 average line and the region 2 average line. We have also here the rated generator speed and the rated power, which is both extracted from the intersection between region 2.5 average line and region 3 average line. If we look up here, it's going to get a bit more complicated. So the reason I have so many different region 2 constants and slopes is that I use different ways to calculate them or to extract them. And the very first one I've already also used in my report. But after talking to Hakan and Ola, I realized that I misinterpreted or misunderstood an information from the report that explained the controller we were currently considering. And I first used the slope of the mechanical torque average line, but they told me that I should consider the electrical torque slope average line slope, which is then represented by this value here. Those slopes of region 1.5 are then resulting from those constants up here. using an equation which is provided by the NREL controller description sheet or paper. And my third approach would use simply the slope of this average line here, resulting in this number. And then I rearrange this equation up here to calculate the constant resulting in this value. On the next slide, we have all values listed again, resulting from my method, considering the measurement data, but also for comparison, I used my method on the set point to look how accurate it was or the measurement data was. And on the very left, we can also see both methods or both data plotted. And we can also see here that, so in the foreground, we have the generated torque set point, and we can see that this graphs, especially concerning the slopes, differs significantly compared to the electrical torque based on the measurement values. That's what we can also see when we look at the different values here. But on the other hand, we can also see that the rotor speeds are not too much differing, are pretty much was equal. I also tried to solve sub-challenge number 3, but I also only found a very simple method which considers the pitch angle. So therefore, this method requires the information from the measurement data on the pitch angle, which is not always the case. But my thinking was that for the controller we're considering, the control mode is constant as long as the pitch angle is not changed when our rotor speed is below the rated rotor speed. So in my case, I assumed here a change in the control mode when the pitch angle was changed, as long as the rotor speed was below rated speed, if that makes sense. And my results are then here on the right side for those time intervals, resulting in those pitch angles changes. So that was pretty much my method. Here are my references. Thank you for listening, and if you have any question, please do not hesitate.
All right, thank you. Well done. Questions? Pete?
Yeah, a very quick one. You decided you were moving into a different region when the slope was bigger than a particular tolerance. How do you pick that tolerance? Was it just something big enough, or was there something else?
Yeah, I picked it from experience. So after looking at some different slides, or not slides, different measurement data, different times, I just picked one that seemed to be working.
Yeah. Okay. Fair enough. Just curious.
Yeah.
In the plots, I saw the orange curve optimal values. Did you?
The orange one, yeah.
Yeah. How you calculate this curve? Did you?
Yeah, right. Sorry.
Did you mention about in this presentation?
No, true. I did not mention it, and I simply used the standard formula, and I set an array with all the rotor speeds with different rotor speeds, and then I calculated the optimal torque. If that makes sense.
Okay.
So just using the optimal CP.
Yeah, and the theoretical values that are considered for this turbine, the optimal CP, optimal lambda, and based on this, I calculated it.
is that information available to everybody? Where did? Sorry, I'm not 100% sure where that was that information provided at the beginning. I guess
maybe
so.
not. I don't know.
I'm not sure.
But I think it was here only for yeah, it didn't have a real impact on. It was just computer.
So what can I just understand as well? Because obviously I didn't write this challenge, so I'm not 100%. So that the results of sub-challenge 1 and 2 is this table here, this list of parameters, which have got a load of numbers for the different areas. Is that correct?
My understanding is. Yes. Sorry.
And what's the answer? Like this is a blind test, right? So I'm assuming. How can I see? I think you're here. He's here now. Is he here? Okay, you are.
Yes.
Yep. Right.
Yes. No.
Is the answer? Obviously, we're not going to say the answer now. But when we evaluate the results, is the idea that we actually compare now this table to the actual values, which in the period of time. Well, you know those values in a certain period of time, I guess. What?
Yes. First of all, Corin has been working with this in parallel with his master's thesis. So he has kind of made a model that worked for the challenge. But of course, during the work in his master's thesis, he knows the optimal CP and so on as well. And that has been worked as part of that's one thing that we wanted to explore a little bit, how the measurements compare with the theoretical values. So, but to my understanding, the method is not depending on knowing the optimal CP and so on.
Yeah. But my question was about something else. My question was, do we have or do you have the answer?
Yes,
the actual values.
I have the values or that we kind of know, but they are kind of tuned. So they are more, you can say, chosen based on generated torque set point, and that is not an exact but quite good comparing with this T electric here, which is very similar to what the RES, Alex and so on used.
Yeah. Okay. Let's move on because otherwise we're going to run out of time. Thank you again, Corin. So who wants to go next? Any preferences?
I'm quite happy to go next if
Alex and Osman, are you okay with that? Yes, he says. Go for it, Pete.
Okay. Right. Hopefully, you should have the slides up.
Coming slowly. No, yeah.
Yeah. Okay. All right. Let's carry on. So, just to keep it fully contained, I just restated the challenge here. So I'm going to be focusing on challenge 2, which is the torque rotor speed lookup table from the data. So before I got started, I thought I'd just have a little snoop around the data overall and just sort of see what was in there. And so I did my usual thing, starting by plotting the power curve. I also had a little comparison between the mechanical power and electrical power. And I wanted to also check, how the estimated wind speed was working. So I plotted wind speed and estimated wind speed. And eventually we'll see, I also got to the point where I was wondering is how much data have we actually got and what's the availability like? So going on. I first plotted the power curve and I was expecting the classic power curve and I got this. So I was a bit surprised at this, but in a way I shouldn't have been because of course this is a research turbine and rather than a production turbine, so there's no real reason it should be following that precise power curve. I also wanted to have a little comparison with the how electrical power and mechanical power looked. So you can sort of see these. Oops, sorry. See these here. It is roughly linear. There are a couple of weird data points, so I did some filtering here. And so again, so effectively what I did here, I extended the data set to add electrical power and mechanical power, and they more or less agree, but not completely. That was really just more for my benefit to sort of understand what the data was like. And then finally, I wanted to sort of see how continuous that data recording was. And so what I did here is I calculated the difference between every pair of adjacent data points, time difference. And so when we get a spike, that represents a pause in data collection. The bigger the spike, the longer the pause. And you can see here, there are quite a few big pauses that occur. And my next thing I did is I thought, well, okay, let's focus on challenge 2. And I plotted the rotor speed torque data sets in each of those individual contiguous blocks. So effectively, wherever we have a flat line here is where I did a plot here. And what I've done here is I've gathered a collection of these. And you can see that the turbine behaves very, very differently depending on which data set you take. So I thought this is all very interesting. Clearly the turbine's being played around with quite a bit. And it took me this long until I actually revisited the challenge because I was wondering, I was effectively thinking about which one of these turbine plots looked like the best to do the to take the challenge on. And I'd had a little look at the challenge again, and I was reminded in the challenge that we were supposed to be using a very particular date set. Now there is a pause in between those two, and so I've done the plots for the first and the second block of data that you can see, and so you can see that there is this little spurious line here in the first part of the data where there's some other behavior that's being exhibited. So the methodology was an iterative filtering. So first filtration was to remove all the obvious outliers. So I removed any data points where the torque was below -1,000 Newton meters or greater than 7,000 Newton meters. I then fitted a k nearest neighbors regression model to it. And then a second filtration pass was to remove any data that was about 500 Newton meters away from that initial regression model. And again, the 500 is just a number I plucked out of air. This was by eyeballing the graph, and I thought 500 was far enough. So then refitting the k nearest neighbor regression model, and from that I generated a lookup table using the observed RPM range. And finally, I then compared that to the set points. So the results we get from there is this is those first two iterations. So you can see here in the first iteration, we have some of the regression curve is being pulled upwards by these data points that are on the spurious curve. But these points are going to be too far away from the regression point. So when we go to the second filtration, we see that these points have been removed. And then when we when we calculate the regression or refit the regression, we see we get a much flatter regression. It still is quite bumpy. It most likely is because I chose 100 centers for the k nearest neighbors, which is most likely too many. We also see some weird behavior here, largely because we've got a lot of data here. It's quite noisy, and so we get this sort of strange looking control graph there. So comparing it to the set points, well, here we get a little surprise, and we can sort of see that there's a significant bias all the way through here. It's not quite constant because the bias in this part here is much larger, but there is nonetheless a bias between the observed data and the set points. However, the slopes aren't too far off. So we've got a roughly flat graph here up until 55 RPM. Then it shoots up. We then sort of see some form of flattening, although it's not quite flattening. It sort of goes down as opposed to continues to go up, and then we get a sharper increase as well towards the end. So just some final comments. So it was all done with bivariate data. The rest of the SCADA data was ignored. The regression model sort of is reasonable, give or take a bias. And there's also that just reminder of that strange data that we filtered out, which we can't really explain by the set points. So that is pretty much it. I'd be happy to take any questions.
Perfect. Thank you. Questions?
Yes, very interesting. So funny how this challenge looked like from the other perspective. So it's really nice. Did you, when you plotted all the data in the beginning, did you do any binning or filtering, or I mean, like, because the data is very high resolution, so of course it's very noisy. It's
Yes, I did some. So if we go back to these ones, I also I did a moving average.
okay.
And the result was more or less the same. A great big cloud of points.
Yeah, you did moving average of both the wind and the power.
No, I just did moving average of the wind.
Okay.
My assumption there was that the turbine inertia would have been riding through the variability of the wind, but maybe I should have tried also doing a moving average on the power.
Yeah, and the power. What did you have for power?
I tried again both of them, mechanical and electrical.
Yeah. Okay. Yeah, I think the mechanical, if you take the main shaft torque multiplied by rotor speed,
yeah,
that is very noisy.
Yes. Yeah. But no matter what I did, I never got the clean curve we see in the textbooks.
No, exactly.
Yeah. So
I don't either.
yes. And it took me a while to appreciate that there was a reason for that this was not a turbine that was being operated to make money, but a turbine that was operated to get understanding.
Yes, and it's a very small turbine, so this how one would do this binning or the filtering, it has to be quite. Even if we filter a lot, it will still be noisy.
Yeah.
So the result is the line that you showed on the previous on the no, not the previous on the line, like.
Yeah. So the result is effectively this red line here.
Red line.
Yeah, that one.
Did you determine some kind of relation between the mechanical torque and electrical torque, or if you say mechanical power and electrical power?
No. No, I didn't look at that.
Yeah.
You're expecting, what were you expecting something particular? Or you wanting
Yeah,
to know?
I mean, we have a generator efficiency of about 0.85.
Okay.
But I mean, so if I would say that the relation between the mechanical torque and the rotor speed should be, so if you would like to compare these curves, one has to sort of readjust them based on the generator efficiency, I think.
Would that be comparing effectively this one here? That's electrical here and mechanical here.
Yeah.
And you can see it's not a complete X equals Y.
No. But
it's
again,
not.
It's not. But I don't know how that would look like after. Or did you do any filtering or smoothing?
No. No, I didn't. No.
And we, of course, that varies with the level of the torque. So it's some kind of curve. This is something that Corin has been struggling a lot with.
Yeah.
That's why. And we maybe I say that. Yes.
Yeah.
Huh? Thank you.
Great. Thank you.
Okay, thank you very much. Let's go to the final one, and then maybe we can, if we've got time, we can have any other discussions that are needed. Alex, are you presenting, or is Osman?
I think Gabe will lead, if that's okay. Gabe?
Oh, Gabe's Yep. I didn't realise he was part of your team as well. Hi.
Yeah.
I thought he was the only observer who didn't take part, but he's not.
It's yeah, the name sometimes gets shortened to Gabe. Well, at least that's
Gabe.
what I go for. I guess it creates confusion. Can you see the presentation?
Yeah.
Yeah. Okay. So yeah, first slide is probably a bit superfluous right now. We've seen it already a couple of times. I'm just gonna skip over it in the interest of time. The way that, well, this is written from, I guess, Alex's point of view. They basically reached out to an internal group and asked who was interested in this challenge. Osman and I were bravely enough to volunteers. And we've created that repository that I think now most of the interesting part is merged into the repository that WeDoWind controlled. So you should see it as one of the branches of that. So the first sub challenge was, as we saw, identifying the parameters, so yeah, 1 and 2 were essentially trying to find those parameters. I'm not sure how much you can see of the little numbers there, but the idea there, and trying to see if there's, yeah. So the way that we solved it was to use, we only used the electrical torque and electrical power. So we didn't, we saw that it was cleaner and easier to work with. So we decided to use that. And we did kind of something similar to what Corin did, which is we plotted the data and binned them with, I actually don't remember exactly what was the X coordinate gap that we used, but bin them to make them a bit more smooth, and then fit a line using this library that essentially does fitting of points. So we let this algorithm that fits lines. We knew the number of splits just by looking at it, so we could tell it how to split it. And what comes out of that is essentially the slopes, the points and the heights. So you can calculate essentially slopes and intercepts from those. And you get that orange line that you can probably see there at the bottom. So as it says here, the one trick is to create a low noise version of the torque, and this was done by, so we saw just before by Matthew, it was showing that there was that very distant across most of the first part, and then there was still some distance between the torque and the set point. So what we did was create use machine learning model, boosted tree regressor to bring down the torque that we see versus the set point. So we could then use only the predicted set point based on the real torque to then bin and fit a line through. So that's how we kind of try to adjust for that difference. Sub challenge 3 was quite difficult. Alex did create these plots, and I think they were really nice and really interesting. What we saw is that, yeah, of course, you have the change in pitch, but you also have change above. Again, I'm not sure how much you can see from the slide, but at the top, on the left side, top middle, you have the generator torque versus turbine speed, and you can see that you have those dips. the plots were used to essentially manually look through and detect where we think there was a change. The most important, I guess, would be probably the bottom one, along with that has a time series as the x-axis, and then the orange and the blue are the normalized torque residual. So using the torque model from challenge 4 and the pitch residual, again, checked against a normal parameter, which was that the value of 2. The values that normalized from are marked in like gray areas. And I think that's pretty much it. So we just Alex went through all these plots and decided where the changes was. So it was a manual thing based on model residuals, but we couldn't find algorithms that would do that part automatically, unfortunately. Not sure if I missed anything, Alex. Feel free to jump in.
No, yeah, that's a good summary. Well, Gabe tried a lot of awesome stuff, which we just didn't quite have enough time for it to automatically work. But yeah, I know these plots are quite busy, but yeah, the bottom time series, you're basically looking for clear steps. So in the example on the left, there's clear steps in the torque residual, which is blue. There's also clear steps in the power itself, which is the top left plot and the middle plot are power. So you can clearly see that rated power is being changed. And then the example on the right has clear steps in pitch, which is the orange residual. So yeah, that was how we did it.
That's the bottom right plot you're talking about. The bottom right, that's the orange steps.
Yeah,
Yeah,
you
so
can
these-
see.
Oh no, that's the left.
But,
okay, the bottom left. Sorry.
Well, it's the same
Cool.
as here.
Yeah, it's the
except
same.
two different
Okay.
periods.
Yeah.
Yeah,
okay.
yeah. Two examples.
Ah,
Yeah,
okay.
each of these are always exactly 1 hour of time. And where possible, I sort of colored the data by time progression. So the yellow is at the end of the hour and the purple is at the beginning of the hour. So in the top row, which are scatter plots, you can look at different parts of the scatter plot and understand what time they occurred. So yeah, to talk through the examples in more detail, I suppose on the left, like the very, very top left plot is a power curve plot. So you can see a yellow power curve, which has the highest rated power. You can see a green zone, which is less rated power, and you can see a purple one, which is even less rated power. Then in the middle top, you can see the corresponding torque speed curves for those changes. And in the top right scatter plot, those are the pitch, that's pitch versus power. So you can see the rated pitch action. And then as Gabe said, there are time series of the same data below that. So that was the format. And then we generated, well, I generated these plots for the entire data set and simply flicked through them. And when I saw a change, I would simply fill in rows in our CSV and describe what I saw. That was, it's not very data sciencey, but you know, sometimes data science is like that.
Yeah, it'd be very interesting to find out when their changes actually occurred. I guess that's what we have to do as part of the evaluation.
Yeah,
That's what I'm
we
guessing
have
you
some
know,
diary
right?
written down. Yes.
But probably your definition of those time periods is probably also like a manual, yeah, looking at a logbook or something.
Yes, that's the plan.
I was going to mention one more thing on challenge 2, if I may, if that's all right.
Yeah, go for it.
I'll zoom in. I think I can. Yeah, when we were preparing the CSVs, we had more verbose Excel file, so we didn't submit all this detail. But the one, well, we're not familiar with the NREL controller, so a lot of this was it was difficult to interpret the parameters. But this one in particular, I was interested in. This is notionally the torque constant, which defines the quadratic part of the torque speed curve. But it sort of looked to us like this middle section was a straight line instead of quadratic, but it is hard to tell. I saw a little code in the NREL controller saying that basically this parameter is allowed to be 0, and then the region 2 torque is flat. So just to explain that, that's why we put 0 in there, but that might be incorrect. Be interested to know how these things were really programmed.
Yeah, I will double check what they actually had. There was a value given in not 0, what I recall, but they are related to each other, so you can calculate from the other values on that line, right?
Yeah, I saw in the NROL documentation you can do that, but you're also allowed to set it to 0. So yeah, again, I'm not sure. For us, we don't work with the NROL controller, so that was quite a big learning curve of the challenge, was trying to learn the NROL controller enough to.
I mean, you can say it like
values.
this, that it is a way to make these slopes in a consistent manner, so that you can calculate. You define the regions essentially, and then those formulas are intended so that you get a continuous relation between the different regions. So, just a very quick question. You sent out a PDF before, and then you presented now, and then you uploaded on the WeDoWind site. I noticed that there seems to be that you show different days of the data.
Different
So
days.
As example results. So
For sub-challenge 1, 2,
yes,
and
for instance
4.
here, yes. So this is one set of data that you show here, and then you have a different that you uploaded on the.
Oh, that's right. Yeah, sorry, I made this slide just now before the call. I have a folder of hundreds of these plots, so I just grabbed a couple.
Okay,
quickly.
great.
So
great.
I could send you all the plots if you'd like them all.
No need. I just wanted to know if there was a difference.
Oh, that was another I was going to say about sub-challenge 2. So I think we were instructed to use September data, but we ended up using June data.
Okay.
June,
Yeah.
from June.
Yeah,
when
because
I wrote,
it
that
had a
was
longer,
just-
it had more variety of RPMs, so we could fill out the entire curve better.
Yeah. This was not something that we discussed so much. When I wrote that date, that was just one date that looked good to start with. So one shouldn't feel too restricted to use that date. And maybe I wrote it in a not so good way. It was not intended to be some kind of to limit your work. It was more, okay, this long data, choose this date to get started.
Nice. Okay, that makes sense. Sorry to interrupt, Gabe. Please continue.
That's all right. I'm going to quickly go over the last one. So for this one, we've kind of what's it called? Re-engineered or back-engineered the logic behind the controller. So what we did was to take the data and to fit essentially those KP, so the gains, KP, KD, KI, as well as 2 extra parameters, KI0, because of course, being an integral, you cannot know what the starting point was when you start your analysis. So we just fitted an extra parameter for it, which is the start of the integral sum, and a low pass filter steps, which is just something that can allow the rotor speed to be a bit more smooth. We do a rolling mean using the parameter of to catch the number of steps, and then we just calculate the wind speed error, so the rotor speed error, and then use that as the value of error that goes into those parts of the PID controller, and then just fit those. So that's pretty much it. And I think the next slide was the result of it. So applying it, we can see the reconstruction in red and the actual in blue, and then the same, but instead of against time or index, I guess in that case we just plot it against an increased number of points. the bottom one is actually the two against each other. So you would expect or hope that this is as straight and as much of a y equal x as possible. The 100 Hertz data makes it so that 25 seconds is 2,500, which is the x-axis.
Sorry.
No, go for it.
Yeah, yes. Did you only use the 100 Hertz data and that was the only one that worked, or did you try the different?
No, we went with the 100 Hertz data because it seemed like it would be more like why settle for less if you can use the higher frequency data. Of course you can try and do it for lower frequencies just in case your data coming in will be a lower frequency. But of course, if you can get it to high frequency data.
I think the 100 Hertz data is just for a very limited time, so that's why you might wanted to have the covering more part of the different.
That makes sense.
Yeah.
Okay. No, we didn't try for lower ones.
Okay.
I think that's it. Yeah, we submitted. Osman will present our results at the Win Europe Tech workshop, and I think that's it. Not sure if Osman or Alex, was there something that I kind of missed that you thought would be good to highlight? Right.
Maybe just want to highlight the suggested period is not usable for the sub-challenge 4 because the pitch is fixed at 2 degrees. Then the period is changed for also in sub-challenge 1 and 2.
Yeah.
Yeah, I guess it's easy to see in our Python code this day in June. I think it was June 9th, wasn't it? June 9th was our favorite day. It had the biggest, like, it had the 100 Hertz data, it had a nice range of wind speeds, it had everything. It's a great day.
Yeah, this is half of the work, is to find the good days.
So the performance of the algorithm is, can you just show me the next page again? So it looks
it's
like
really impressive.
Really good. How did you quantify that? Have you done an RMSE or something over the whole time, or what have you quantified it?
Oh yeah, to fit it, we fitted this. I don't know if this is the actual. Oh yeah.
So mean absolute error of 0.16 degrees is it's just for for those 25 seconds. And then go on Gabe about how it's fitted if you want.
Yeah, so the error was quantified, as Alex said, with mean absolute error, but you can throw a bunch of metrics at it. It's just essentially just the red line versus the blue line, and you can decide how to define the goodness of the fit. But the way that we created the red line is essentially using this function. This is essentially the logic that we reverse engineered, and by just telling it to be the way the metric that we used for the fitting was the squared error of essentially the reconstruction versus the mean squared error of the reconstruction versus the actual.
Yeah, you just give it to SciPy optimize, and it then spits out these optimum values you can see on the slide. But yeah, the overall performance mean absolute error is less than 0.2 degrees, which is really good for 100 Hertz data. I think a lot of this was like guessing what the different variables were. Like at first, I thought U of T would have been the pitch rate rather than pitch, so that was like a wrong path. And also realizing we had to add in a low pass filter emulation was another thing that, that this is like the finished product, but there was a lot of trial and error to try to figure out what the controller was doing, if that makes sense.
And does it work for other time periods as well?
I think we tried it on other time periods. We were kind of low on time, but yeah, this is the formula for that error. to calculate to optimize on, and this is literally the optimization cycle. This is already in the WeDoWind page in the chat, and just above is the thing that we were putting in the slide.
Okay.
And that's the pivot.
All right. I actually wanted to discuss a few other things. We've got like 6 minutes. So, well, anyway, thanks to everybody for all the work. I mean, we had 3 submissions, which is, I guess, about the minimum to have a decent conversation about it. But I think it's still good to have these three different submissions. We have this evaluation panel, of which Hakan is the only member who is here right now, which I'm a bit disappointed about, to be honest. I mean, I'm happy that Hakan's here, but the others have been. We've got a meeting to discuss the evaluation, and they've been invited, and they've been given access to the reports. But in the worst case, it'll be Hakan's assessment. The thing is, the Chine's provider, he's probably the most important person anyway. So, and yeah, we would discuss what to do with these. If we really want to do a evaluation in the sense of first, second, third place, or not, or how we want to do it, or how we're going to do it, we need to still sort of work out. And then you'll all get a participation certificate and a mention on the some announcement from EAWE that we do. You have to. So there's 2 things that you should do. You should put your code on GitHub if you've got any that is usable. I think Alex and Gabe already put the link in theirs. I guess you have access. So the process was supposed to be, we give you access if you've registered in that document, and you put your GitHub usernames in the registration document. If someone tries to do it and doesn't have access, just tell me, and then I'll sort that on. And the other thing is the participant survey, which it's just a small thing, but we use it to track WeDoWind and how useful it is. And I haven't actually adapted it yet for you. I just need to quickly copy and paste it from a different challenge, and I'll let you know when that's available. And then the other thing to discuss is a paper. So Alex and Gabe already mentioned that they submitted the work to a conference. So the general idea from these WeDoWind challenges is that we do something together. So the other challenge that just finished, where there were like 5 participants, four of them have said they want to actually submit a proper paper on their work, like a journal paper, because it's quite a lot of work. And then we decided we were going to write one collaborative paper, which I would lead, and I would sort of make a comparison, and then also talk about WeDoWind and how WeDoWind helps in bringing people together and stuff like that. And the trouble is with the collaborative papers, you don't have much space. You have to do quite a short summary of the results, because you can't have a massive analysis of 5 different results. Okay, in this case we have 3. So that would be my question. Like, what do you want to do? Like, do you want to participate in a collaborative paper where we talk about what we've done? Do you as well want to publish your separate results? Like, how do you feel about that?
I don't think we're planning to write a paper. We were doing this for the learning opportunity, and I think if there's something collaborative, I think we're open to continuing, like contributing to a collaborative paper. I think we're open to.
Okay. Good. About the others, Pete and Corin?
So quite similarly, I did this for the fun, and I think what I've really gotten out of it is just listening to other people's approach to effectively the same problem. So I wasn't planning on any papers coming out of this. I suppose part of it, me thought that the problem was a bit simplistic. I mean, I only did the easy one, of course. But if anybody has an idea for how to go about doing a paper and they want input, I'm happy to help.
Yeah, okay.
I'm not quite sure if I fully understood the paper thing, but I mean, I'm currently writing my master thesis on this topic until June. But I don't know, does this have anything to do with the paper? Or I mean, does this, how do I say? Is this a problem, or is it like difficult to do a master thesis and the paper, or how is it meant to with the paper collaboration?
No, I don't think it's a problem or difficult. So I can, in the chat, I've put an example of what we did for a previous challenge where we've got different examples, but this is just one of them, where we had the paper was based around the story of we're trying to get people to work together and share knowledge and learn from each other through WeDoWind. But then it actually introduced all the results as well. And then it summarized what some of the difficulties were with trying to work together or collaborate or learn from each other. So it was more, the story was more focused on let's try to get people to learn from each other. And this was the challenge we did to do it, rather than actually on the details of the method. So if you want to write a paper at some point about your master thesis, or anyone else wants to write a paper about their methods because it's important for you to publish your methods, then you could do that separately. I have just gathered that you're not really bothered about that part, but that's what other people in the other challenges have wanted to do. The collaborative paper would then, if we do one, and that would require me to initiate it, would be more focused on this whole story. Like WeDoWind is great. Even the part of, like in the previous one, we also looked at the participant surveys, and we said the main thing that they gained was learning from each other about the method. Like Pete just said, if you put that in the participant survey, then I can read what you put and I can shape the story around that. But it's important for me to publish success stories of WeDoWind so that we can get further funding to do more stuff and we can attract more people. So it'd be more like from that point of view, rather than, yeah, we developed a new model for the controller. Like we don't really, we want to show that we created some value, but it wouldn't be focused on the science part. So
Yeah, okay, I don't know. I think I would like to talk with Håkan and Ola about this first, and then
that's fine. We can do that. Also, I
Okay.
haven't got that much time to think about it in the next couple of months anyway. So if I was to do something, it would be a bit later anyway. So I can always just get back to you.
Yeah,
Well,
but did we have a plan to meet at the end of April to sort of follow up this?
Yeah, I mean, so we've got an evaluation meeting at some point, which I can't remember when it was. Is that what you mean, or do you mean with the participants?
Yeah, I thought that was with all of us, but maybe that was just we who are to. There was I just get the invitation. I don't read them too carefully.
Yeah, so the 28th of April, that's the evaluation panel meeting. So the idea of that is to actually decide on the evaluation.
Okay. I thought it was feedback for this.
No, I think we do that on the 28th of April, and then we'll be in touch with you again about what we want to do and ask you what you want, how you want to proceed. Okay.
No, but I will read and think, and I am really happy to see the three different ways of thinking about it, and I really like this comparison of using sophisticated tools and sound judgment. I like the engineering thought put into it. I'm really happy to see your presentations. So thank you very much. And I saw Corin's yesterday, so even though if I wasn't at the start, then we heard. I'm good.
All right, I better go. Okay. But thanks again, everyone, for your contributions.
Thank you very much, and thank you,
I'll be in touch.
Especially those that submitted. Yeah.
See you soon.
Thank you. Goodbye.
Thank you.
Bye.
Bye.